Well, good afternoon, everybody. Pleasure to see you here at 315 Chestnut Street in Philadelphia and also online, where I think we have people dialing in for this program from all over the world. Pleasure to have you here. I'm David Cole. I'm the president and CEO of the Science History Institute, and I want to welcome you to the next installment in our Joseph Priestley Society lecture series. We have an exciting program for you today under the title of Electric Vehicles, and we reached the tipping point. So speaking to an issue of sustainability and the innovation around that and where that stands at present, we're looking forward to that talk. And I just want to offer another program note on that front on the theme of sustainability. It is in 2 weeks that we'll be presenting our annual TT Chow Symposium. Our TT Chow Symposium talks on the intersection of chemistry and sustainability. And the theme of this year's TT Chow Symposium talks will be on looking at innovations in water, new technologies around water, and all of those being sustainable. And we're looking forward to that program. That will be on at 3 o'clock Eastern time, for those of you dialing in, not on the East Coast, 3 o'clock Eastern US time on Tuesday, November 15th. So mark your calendars for that, 3 o'clock Eastern time, Tuesday, November 15th, when the TT Chow Symposium will present 4 interesting talks and a panel discussion focused on sustainable innovations around water. Looking forward to that. And finally, let me just say that we're bringing the Joseph Priestley Society talk to you today, courtesy of the support that comes from all of you. So many thanks. We offer these programs free, online and in person. Many thanks for what you do to make that possible. And as we move into the season of giving in the next 2 months, I want to encourage you to think fondly of this program and of Science History Institute. We always appreciate your support of our programming and our mission. So thank you very much for that. And with that, it's my pleasure to introduce our program chair, Bill Tazinski, who's going to tell you a bit more about today's Joseph Priestley Society program. Bill, take it away.
All right. Thank you, David. I will keep this short because no one's here to hear me speak. Everyone's here to hear Becker speak. My first charge to you is, if you are in person, turn your ringer off. If your ringer rings during the program, you are emceeing the January meeting. If you are at home, you have no such restriction. Just keep your microphone muted. Again, welcome. It's great to be here. It's a hybrid program. We have some 30 of you registered in person and close to 200 people online. So speaks to the popularity of the Joseph Priestley Society, and I'll see if I can get this right. There we go. I'm pleased to introduce Dr. Ed Becker. As a longtime employee of General Motors and has worked in that area and then retired and started his own consultancy. Ed is a past president of the Society of Tribologists and Lubrication Engineers, and he also teaches an 8-hour course on electric vehicles. I did make him promise that he was going to keep this presentation under 8 hours, and he agreed. So we're pleased to do that. And with that, I will turn the podium and the clicker over to you.
Thank you, Bill. Thank you, David. Introduction. Let me see, are we rolling straight in? Yes, we are. Good. So as I was joking earlier before we started with some of the early arrivals, anytime a presenter has a question mark in their title, pretty good clue they're not going to answer the question. I'm going to present a lot of evidence, and you may be able to conclude what I think, but I really want you to draw your own conclusion at the end. As mentioned, this is me, professional engineer. My PhD is from the University of Michigan, and I now run my own consulting firm, and there's my email address. I'll show it to you again at the end, if you don't write it down now, but it's just the name of my company at gmail.com. Because I love getting emails and I respond to them reasonably quickly. And ideally, if you have a question or two, feel free to fire them off to me. Okay, with that, I want to give you a brief history. Since there's a historical society here, I want to start off with some history, development of automotive powertrains. And the short Cliff Notes version of this is what goes around comes around. Self-propelled vehicles appear as early as Galileo's notebooks. They go back, the question who invented the automobile is hotly debated and goes back a lot further than you might think. So I'm not even going to attempt to answer that, but we all pretty much agree that the automotive industry began in 1885 when Carl Benz patented his motor and began to produce vehicles commercially and sell them. So all of those other inventors might have been tinkering in their own basement for their own amusement. This was the first attempt to actually commercialize automotive transportation, and a very successful attempt at that. I shouldn't point out, of course, the successor to Carl Benz industry continues very much in business today. Although Benz's motor wagon ran on an internal combustion engine, very quickly, steam or external combustion, if you will, and electric motors became very popular. In fact, electric vehicles outsold steam and internal combustion engines cumulatively from about 1885 to about 1900. So in fact, the first big technology was electric motors in vehicles. There's a photograph of Ben's three-wheel motor wagon from 1885, as I say, the beginning of automotive, and it was an internal combustion engine. And it has a lot of advantages. As it says here, it can run on a variety of fuels. It's relatively inexpensive. Internal combustion engines are made primarily of iron and aluminum, two of the two most abundant metallic elements in the Earth's crust. I say relatively reliable. Nothing was terribly reliable in those days, but if you understood the basic principles, getting down and crawling under and getting it running again was part of the sport of motoring, what we would now call an extreme sport motoring in those days. Because the energy density of these, particularly liquid fuels, is so high, you got good range from the beginning. You can go a long way on a single pack of gas or diesel or whatever. It turns out you can burn just about any fluid. And it's easily refueled very quickly, as fast as you can pour from one container to another. And the nice thing about an internal combustion engine is you have power available to the wheels on start. Downsides, the internal combustion engine has a limited range of RPM, and it develops its highest power at higher speeds. So to get power to accelerate, you need to run the engine quickly while the car is going slowly. And to get power to maintain speed, you need to run the engine quickly when the vehicle is running quickly. You have to vary the ratio between the engine and the wheels. So you have to have what we call a transmission. That's a given with an internal combustion engine. And the other thing about internal combustion, it generates zero torque at zero speed. If you stop the vehicle and you don't disconnect the motor from the wheels, it will stall and you have to restart it. So not only do we need a means of altering the ratio of speeds between the wheel and the engine, we also have to be able to disconnect the engine from the wheel. And that's where the clutch comes in. Now, the big disadvantage is that the internal combustion engine is not self-starting. You can't just put fuel and spark to it and get it turning. You have to put external energy in. Typically, and originally, that was by means of a hand crank. You've probably all seen the pictures. In fact, why do we still call the position when you turn, if you still have a key, we go from off to accessory to on to crank. Why is it called crank? This is why, because you hand cranked it originally. And generally speaking, I realize there are some gimmicks out there, but generally speaking, the internal combustion engine can only turn in one direction. You can't run it in the other direction. So if you want to back up, you have to have a means of reversing the rotation as you send it onto the wheel. So yeah, more gears are required. Well, here's the 1912 Stanley steamer, or modern restoration of one. Steam was pretty popular at the beginning, and for a lot of reasons. I said the internal combustion engine is tolerant to fuel. The steam engine can literally burn anything that will burn will fuel a steam engine. Fuel quality is not terribly much interest, at least in these days, before we worried about emissions and such. And it was a mature mobile technology in 1885. That's what steamships and railroads ran on. So it was well understood. And of course, the steam engine itself goes way back beyond that. It generates high power at all speeds. So it can generate good power running slowly and good power running quickly. You don't need a transmission. And you have power available at 0 speed, and you can run it backwards. So you don't need gears. Problem, it takes time when you light the fire in order to boil water. You all know about the saying of a watched pot. It can take a very long time to develop power. It has the lowest thermal efficiency of the technologies we're going to talk about. Typically for these early cars, maybe 15% of the energy that you consume by burning the fuel actually move the vehicle. That's a non-starter for today. External, you're not going to hear about external combustion because it's just inherently low efficient for mobile platforms. Higher maintenance than internal combustion engines, and not only do you have to carry fuel, you have to replenish the water, or you have to have an onboard condenser, which adds complexity and weight. You have two fluids to maintain continuously instead of one. And then we get to the electric motor, and again, these were quite popular. This is a 1913 Roush and Lang that I took a photo of in Spokane, Washington, I believe. And I actually had the opportunity to not just view this from above, but while the docent wasn't looking, I crawled underneath and took this picture because I want to highlight here the simplicity. Here's this box. Let me get my pointer going. There we go. That's the electric motor right there. And it just runs on current from the passenger compartment. You increase, decrease, or reverse the current. Here is the drive shaft, which comes into a worm gear, and what anyone familiar with rear-wheel drive vehicles recognizes as a standard differential. This is just a means of splitting the power between the two rear wheels so that they can turn to different speeds when you're cornering. That's it. This is the entire drivetrain. It's quite simple, so that's a big advantage, as I talk about. It generates high power at both low and high speeds, and we'll talk about that. So a transmission isn't required. I may mention that some people are starting to add gears in order to improve efficiency of these motors so they can run closer to their peak efficiency more of the time, but that's optional. I think BMW is the only one that has one in production, a multi-speed transmission. All the rest are single-speed transmission, easy operation, low maintenance, high power at low speed. It can run in reverse, so the wheels and the motor can be permanently connected by means of the gear. And in addition to the motor converting electricity into mechanical power, the motor can run as a generator, meaning instead of using mechanical brakes, you can run the motor in reverse and actually convert the kinetic energy of the vehicle back into electricity and recharge the battery. Call that regenerative braking. Partially is the word in parentheses. I'll tell you, typically 60% or so efficiency is what we see in these regenerative. Very important for when we talk about range. Extremely quiet and extremely high efficiency. We'll talk more about that. Disadvantages. Now we're talking, 1900 here. The disadvantages were high initial cost. These vehicles easily cost twice what an internal combustion engine did. Limited range. Long time to recharge, a lot longer than it takes to fill a fuel tank. And if the battery needs replacement, those were inherently expensive because they're made of more complex and expensive materials than just iron and aluminum. Okay, you may have heard this. Who killed the electric car? Allow me to introduce you to the gentleman who killed the electric car. This is Charles F. Boss Kettering, founder of the Dayton Engineering Laboratories Company, better known by its acronym DELCO, after it was acquired by General Motors, and he became the first head of GM Research. He did not invent, I see this in print that he invented the electric starter. He did not. I want to be very clear about that, but he developed the first mass-produced electric starter. And that was pretty much the end of electricity for cars, because up until then, the biggest danger was that hand cranking of the vehicle. It was inconvenient, it was dirty, it was quite dangerous. Broken wrists and forearms were common. And now that you didn't have to do that anymore, along with the automatic transmission, which came on later, but the electric car was already dead at that point. Now you no longer had to manually adjust the gear ratio between the engine and the wheels. It was done for you. So we have a dearth of electric vehicles from about late 1920s up till 1996. And I will somewhat parochially attribute the rebirth of the electric vehicle to the GM EV1 in 1996. I should point out that Toyota very quickly followed with an electric version of their RAV4 in 1997. Ford bought a Norwegian company called Think that was making commuter cars, electric cars, about the same time. And within about 5 years, all three of those companies abandoned electric vehicles again. Certain things were just not quite ready for prime time, as it were, but they never left the public consciousness. The idea that electric cars were possible and possibly even practical caught on about this time. Well, one reason that they have remained is I want to talk about a few different architectures. I've already mentioned the internal combustion engine at the top and what I'll call the battery electric vehicle at the bottom, but in between we have these things called hybrids. Now, when I started with the industry, a hybrid was a combination of a standard vehicle and a truck, what we now call an SUV. We call those hybrids. The word hybrid has been used to describe different technologies, but now it's an electrical and an internal combustion engine hybrid. And we go through various stages, and I'm not going to spend too much time on this. I just simply want to talk about what I call here the full hybrid, or HEV, which is a vehicle that can run on either an internal combustion engine or an onboard electric motor. But I'll talk about the only way that it has a battery pack, but the only way the battery pack is charged is by the internal combustion engine. And the way this gets its efficiency is it allows that internal combustion engine to run at or near its peak efficiency most of the time and greatly improve the fuel economy by storing the excess energy in the battery. Now, the plug-in hybrid, pretty obviously, now we can charge the battery externally in addition to having the motor charging it. So since hybrid vehicles have both a conventional engine and some electric motors, we need a control system to divide the torque between the engine and the electric motor on demand. It's more complex than either an electric motor or an internal combustion engine by itself. Generally, it's heavier because of all of the additional componentry, and not least of all, it's going to be more expensive than an internal combustion engine because two motors are always going to be more expensive than one. That's the way I would put it. Now, the pure electric vehicle, as I've already mentioned, has the advantages of high efficiency, instant torque, high torque at low speeds, and the ability to recover some energy during braking. So these are the technologies, the architectures that we're dealing with. This is a full hybrid vehicle. What we see here is you have your conventional internal combustion engine, and then you also have your electric generator, and you also have your battery pack. Just kind of notice the relative size of the battery pack here, but the only place that we put anything into this vehicle is through a standard filler, fuel filler. Hybrid, now the battery, we have, in addition to a somewhat larger battery pack and the fuel tank, in addition to our fuel filter, we have a charging port where we can charge that battery. Typically, these vehicles are able to run somewhere around 40 to 60 miles, surely less than 100 miles on the battery alone before the internal combustion engine kicks in, because you have, because basically the size of the battery pack you can accommodate while accommodating all of this other hardware. But if we do away with the gasoline engine altogether, now we need a much larger battery pack. You can see typically it occupies the entire floor of the vehicle. But now we've done away with our fuel filler port. We just simply have our charging port. So that's basically been the progression. And what we're going to see is that a lot of these electric vehicles are becoming, the pure electric vehicle is becoming, it's going to overtake the hybrid. Right now, they're more or less neck and neck in terms of sales. You can buy either one. But I want to focus on what makes the electric vehicle possible, and that is the electric motor, which is basically, I won't read the whole thing, it's a device that converts electrical energy into mechanical energy. That's basically it. And this is an example. This is the motor here, and what you see here is the gears that I mentioned before. Typically, a motor that's of the size that can operate an automobile, we find that the dynamics of such a thing, usually it has a top speed of somewhere around 18,000 to 20,000 RPM. That's fairly typical of these machines. Well, a car going down the freeway at about 60 miles an hour, you work it out, the wheels are turning at about 1,000 RPM. So we don't connect the motor directly to the wheels because to get peak efficiency, we run around somewhere around half to 2/3 speed, which means we want the motor turning around 9,000 RPM when we're going down the freeway. So this is a reduction gear, typically somewhere in the 6-to-1 to 10-to-1 range. And as I mentioned before, usually permanently connected to the wheels. So how does this work? Well, I mentioned repeatedly that electric motors are very simple, so let's build one. What I have here, this is one of these rare earth permanent magnets in the shape of a disc. Put that there. Because the way, as I'll talk about in a moment, what an electric motor does is it uses the interaction between an electric field and a magnetic field in order to generate a force. So my source of my magnetic field in this case is a permanent magnet. My source of electricity is going to be a standard 1.5 volt Duracell battery. And in order to get that current flowing, I need a current path. This is a copper wire, which I've bent into this more or less weird shape. The important thing is it has to make contact with the battery at the top and the magnet at the bottom. And if I've done this right, oops, little tricky. There we go. It illustrates several very important points. Not least of all, I'm going to leave this out here so if you want to play with it. The neat thing about it is when I did this, you'll notice I didn't have to push it to get it started. It starts by itself. So that's a big advantage that this has over the internal combustion engine. And it works by means of this interaction between the magnetic field represented here by the vector B, the electric current by the vector I, and the force that is the mechanical force that is generated is the vector F. It's simply the cross product between the current and the magnetic field. I'm not going to get into vector geometry here. Just simply say that let's just treat that as a multiplication sign for now. Ideally, what we want is for the current and the magnetic field to be at right angles. That's where you get the maximum interaction. And if you do that, you get a force. If my current is good old right-hand rule, my current is running to the right here and my magnetic field is coming out of the board, the force will be upward. Basically, they're three orthogonal or mutually perpendicular vectors. So this gives us the basis of the electric motor. If I want a lot of power, what I want is a good, strong magnetic field. I want B to be big. And I'll talk about how we achieve that. We want a lot of current. So we have not just a single wire in most of these motors, but lots and lots and lots of wires wound together so we can get a lot of current going in order to generate a force. And another nice thing I didn't mention compared to the internal combustion and the steam engine, which typically are reciprocating engines. In other words, a piston moves back and forth, and then we have to convert that motion into the rotating motion of the wheels. So we need a device called a connecting rod and crankshaft to do that. So that's more hardware. The nice thing about these motors is they can be constructed, as this one is, to generate rotational energy directly. So we don't have to convert the back and forth into rotation, aiding the mechanical simplicity greatly. And this was just an illustration. These are two different General Motors products. On the left is a Corvette engine. I think I have the year there, 2000 and something. 2009. Roughly speaking, it's about 200 parts go into making that engine. And this gets in, now we can get into the argument of what's a part, but is an engine block a part, or is an engine block casting and plugs and screws and a whole bunch of inserts? We can go on, but the point being, this is a whole lot simpler. The electric motor, which is generating torque or rotational energy directly, is a whole lot easier. Now, this particular motor here is using these rare earth permanent magnets, which you can see are inserted into the slots on this particular part of a little bit of nomenclature. The part that rotates in the motor is called the rotor, simple enough. And the part that houses the rotor and doesn't rotate, that remains stationary, we call the stator. We have the stator on the rotor. And that's pretty much what I have here, except in my case, it's the magnet is the stator and the current carrying component is the rotor. We reverse that usually. I'll talk about why we do that. These are the basic components of that electric motor, the rotor and the stator. So as I mentioned, we need to have both an electric current and a magnetic field for this to work. One way to have that magnetic field is what I illustrated, where the rotor has permanent magnets mounted in it. But if you recall a fellow by the name of Tesla, whose name has also been in the news of late, he showed and basically exploited the fact that an electric current moving through a conductor also generates a magnetic field. So another way to generate a magnetic field is by having current flowing not just in the stator, but also in conductors in the rotor, which then induce a magnetic field, which then can be used to push the rotor around. So we have these two different types, these two basic types, the permanent magnet motor and the induction type motor. I want to talk about their comparative advantages and disadvantages, not least of all. Magnetic field, when it's generated with permanent magnets, these magnets are mounted in the rotor, which means we don't have to provide electrical energy to the rotor to get the magnetic field. We don't have to have an electrical connection to the rotor and maintain it in this moving part. It's much simpler. It also is more efficient because in the case of the induction motor, to generate the magnetic field in the rotor, I need current. I need to have a way to keep that current flowing as the thing is rotating, brushes or brushless motors, what have you, but some form of continuous electrical connection. And since I'm running current through wires of finite resistance, I'm using energy when I do that. The induction motor of the same size is always going to be less powerful and less efficient than a permanent magnet motor of the same size. So if I want to have the same power output in my vehicle, and I want to use induction, I need a bigger, more expensive, less efficient motor. But this is the part they never tell us about when we're studying engineering, and we really do. These permanent magnets, the ones that we typically use, are based on rare earths like neodymium, dysprosium, and terbium, whereas these induction motors are based on steel and copper. Steel and copper we buy on the order of tens to hundreds of dollars per ton. These rare earths, like last time I looked into it, neodymium was going for hundreds of dollars a pound, dysprosium twice that, and terbium 10 times that. So when you're talking, we may be only talking a few pounds, maybe 8 or 10 pounds of magnets in these motors. That's a lot of rare earth, and they're considerably more expensive. Nevertheless, what's really driving all of this is efficiency. We want our vehicles to have the greatest possible range in a given package. So we want them to be as efficient as possible. At least one source is forecasting that there will be growth both in the non-permanent magnet motors, which are the induction motors, and the permanent magnet motors over the next decade and a half or so, showing where we've been. Both will continue to grow, but the gap, the permanent magnet motor is by far the solution of choice in the industry. Well, here we are now when we survey customers. This data is from 2017, but I think it's still reasonably current. When we survey current customers and say, what concerns you about buying an electric car? You remember, I mentioned 4 things in 1900 that bothered people. High initial cost, still number 1. Limited range on the charge, range anxiety, still number 2. And limited access to plug-in stations. We can talk about that in a minute. And if the battery does die, it's darn expensive. Now, and we also have lengthy charge times there. So this is another one of the more things change, the more they stay the same kind of argument. We still have the same anxieties that we had. And it is today's engineering challenge to address those to the point where these are not barriers in the mind of the consumer. I do want to talk about what has gotten us to this point, and one reason why we're doing this and why I think the electric motor is the ultimate solution. The important point about these two charts, this is the efficiency of an internal combustion engine vehicle on the left and a electric vehicle on the right. And the important thing is here, the left-hand chart, we read left to right, and the right-hand chart, we read right to left. So if we start at the two outside bars, that's the total energy we're putting into the vehicle. Now, I'm not getting into extracting oil and refining it or how we make the electricity, whether it's through fossil fuels or renewables or something else. Point is, we load up the vehicle with 100% of something, some form of energy. What happens in the internal combustion engine is right away we have that brown bar labeled heat loss. This fellow by the name of Carnot, I forget his first name. If you ever studied thermodynamics, he said that the problem with heat is it's the most disorganized form of energy there is. And if you try to organize it into mechanical work, you cannot do it perfectly. You must reject some of that heat. And there, in fact, is an absolute fundamental limit called the Carnot limit for a heat engine operating between any two thermal reservoirs based on the temperature of those two reservoirs. For the internal combustion engine, something like 60% of that energy gets rejected as heat, either through the coolant or straight out the tailpipe with the exhaust, and never becomes usable energy. So we're throwing away 2/3 of the energy of gasoline or diesel. It's getting closer to half, to be fair. That's pretty high, but Carnot says we've done pretty much what we're going to be able to do there. Now, of course, we do have losses in the electric vehicle. Anytime you push a current through a wire of finite resistance, you have some heating and some loss, but it's not 60%. It's more on the order of 10 to 15% in these vehicles. We still have friction in the driveline, but because the driveline in the electric vehicle is much simpler, it's that permanently connected gear set. We're not shifting, we're not speeding up and slowing down those gears and getting all kinds of churning losses in it. The driveline resistance is much less in the electric vehicle. A typical number is that for an internal combustion engine, about 15% of the energy actually moves the vehicle. In the electric car, it's more like 80%. So we have that going for us. We don't have to have a battery that holds as much energy as a gallon of gas. It just has to hold about, what would that be, about 6 or 7, 1/6 or 1/7 to get the vehicle to go the same distance. So that's working for us. And I want to consider where the biggest bang for the buck is. This is one listing of, from 2021, the top 30 light vehicle sales in the world. It has been true for, I've got to go back and look, it's been at least 15 years that China has been the #1 vehicle market in the world. They account for roughly 30% of all vehicles sold. United States is #2, accounting for roughly 20%. And the rest of the world is the other 50%. I will sometimes joke with audiences that if you are not in China and the United States, you're not in the car business. Of course, there are many.
These are all electric vehicles?
No, these are
Combination.
This is combination.
But light vehicles mean cars and small trucks?
Cars and small trucks, yes. I would have to go to the actual publication to see where exactly they drew that line. But for automotive transportation, China 30%, USA 20%, rest of the world the other 50%, broken down among these others. And some of these countries have actually set out formal goals for doing away with emissions from internal combustion engines. And you can see them broken out in color codes. China appears a couple of times on here. In 2035, they basically are saying they're not going to sell internal combustion engines anymore. And you will see, unfortunately, go all over this, you're not going to find the United States on here. The US as a nation has no formal pledge. Now, that doesn't mean there aren't articulated goals. And it doesn't mean that there aren't pockets within the United States, most notably California, that have clearly stated their goal to get out of internal combustion engine business. But as a nation, China has definitely made the most aggressive stance that's likely to have the biggest impact in the short term. And of course, if you're going into China and you're selling all electric vehicles there, you're going to want to increase your market share in that in other parts of the world. You want to utilize your factories efficiently. You want to sell that in the rest of the world by default. there's a good chance that a lot of companies are going to take that same decision, and many of the largest automotive companies in the world, including General Motors, have stated publicly that their goal, this is not a law, but their goal is to stop selling internal combustion engines by 2035. So we shall see
CEV stock.
zero emission vehicle. That means they want to get rid of all internal combustion engines in the country. Now, keep in mind, a good point, the difference between sales and stock. In the United States, and I think this is true of the rest of the world, the average light vehicle on the road today is between 11 and 12 years old, which means if we stopped selling internal combustion engines today, in 2034, half the cars on the road would still be gasoline and diesel. So we're talking about something that's going to be a generation at least in making the total transition. Because, well, durability and reliability have been driving the market for a very long time. But now I want to, since you mentioned electric vehicles, let me talk about that. The biggest market share of electric vehicles is in China so far to date, with all of Europe making, this chart is a little confusing because they have a bar for all of Europe and I have Germany, France, United Kingdom in there. I'm not quite sure how those stack up. But the point being, if we think of Europe as a market, they have the second most, then comes the United States, which sounds nice. Remembering that China and the US are 50% of the market. But considering the rate of adoption of electric vehicles, if we look at the share of, these are plug-in electric vehicles, which includes hybrids, as a share of the population. And you may be aware of this if you're watching the Super Bowl last year, because Will Ferrell did a nice commercial where he lamented the fact that Norway is way out in the lead in terms of adopting electric vehicles on a per capita basis. And it's sort of interesting that it's Norway, Iceland, Sweden, the Netherlands, these cold countries that are the ones that are way out there in the lead. Well, I can sort of understand Iceland because they have tremendous geothermal electrical generation. It's practically, I don't know this for a fact, but it's practically free. Alcoa has a big smelting plant there, and it's not because there's a bauxite in Iceland. There is not. They have to bring it from places like Jamaica. But the recipe for aluminum is bauxite and electricity. And the electricity is basically, they're getting it very, very cheap. It's actually worth it, truck that's to ship that stuff all the way to Iceland, and then the aluminum all the way back. And unfortunately, after finishing praising China and the US here, where do they come in on a per capita basis? We're way down here. Now again, this is 2020, and it's showing the US at around 2.3%. We're starting to see numbers up around the 5%. And with all the pandemic slowdowns and chip shortages and all of that, it's really hard to say what's the tail wagging the dog here. We are probably going to see a significant growth in that area. And what this is BNEF has forecast what the growth will be in vehicles overall, and that's the gray bars where you can very clearly see the pandemic, what that did to us in terms of total vehicle sales. But we're climbing out of that pretty quickly, and vehicle sales are going to be growing again past their historical highs. So personal mobility is a good business to be in. As the bottom line here, it has been for a very long time. But what we are seeing is now the light blue bar in the center here. These are hybrids, both plug-in and traditional full hybrids. What we see happening is that blue bar, that light blue bar, although it continues to grow, it does not grow very fast. So all the growth is in this green bar, which is the battery electric vehicles that we see from here through, they're forecasting out to about 2040. And this is the same data on the right here. What we basically see is the share of internal combustion engines falling, that's the gray bar, the share of electric vehicles rising, and the crossover taking place somewhere around 2037, where electric vehicles start to outsell conventional vehicles. And you see this dark blue bar at the bottom here, labeled fuel cell. I will say a few things about that. But what are we doing to overcome those barriers I mentioned before? Well, the high initial cost, interestingly enough, we look at what a gasoline powered car cost in 2017 and what's forecast to cost in 2025. Not shockingly, the price goes up. Yeah. Probably all familiar with that, but we're probably going to see the average gasoline powered car selling in the low 20,000s for this particular comparison, and a similarly sized electric vehicle. Based in 2025, one way we look at the price of batteries is we talk about how much it costs per kilowatt hour of capacity. So just like we talk about gallons of fuel, we talk about kilowatt hours of electricity. Right now, rather in 2017, it was about $205 per kilowatt hour of battery. And the battery is the most expensive component in the car. By 2025, that's forecast to get down to about 130 and perhaps be cut in half. Excuse me. If that gets down to 130, there are two different forecasts here. What we see is the price of the electric vehicle now also being in the low 20s. And the magic number that everybody keeps throwing around is $100 per kilowatt hour. If we can get to that by 2025, now look at where the electric vehicle and the gasoline vehicle in 2025 are. They are now the same price. The type of batteries that we are familiar with in our cars are the old lead acid batteries, which were the power plant for electric vehicles right up through the GM EV1. First EV1 ran on lead acid batteries. Limited range, high cost, and long charging times. Now we're using these lithium-ion batteries. They cost more, but they have better energy density and they can be charged faster. We'll look at some of that information. I mentioned if we can get down to the $100 per kilowatt hour somewhere around 2025, if we look at the actual historical data on the cost of a lithium-ion battery pack, those are the blue triangles, and what that's done since about 2010. You can see we started out somewhere around $1,200 a kilowatt hour. Pretty big jump to get down from there to the 100, but we continue to improve. I think it says here that it's an 18% learning curve, but we've been cutting the price on that by about 18% a year. And if that continues, the implied price in 2024 is only $94 a kilowatt hour. And by 2030, 62, there's actual reason to believe we can get to where it's competitive. But another concern we have is charging time. We have all gotten very used to the idea of driving our vehicles over long distances, and if fuel gets low, we pull off into a convenient fueling station, and in a matter of minutes, we're back on the road with our charge renewed. Well, originally, these vehicles were charged on household current. And to this day, and when you buy an electric vehicle, you will probably get a 110 volt plug that you can attach to your vehicle and plug it in at home. So your typical 110 volt, what we call a level 1 charger. If we consider that that puts in about 1.4 kilowatts, let's see, that was in terms of, 1.4 kilowatts in a minute will add to a typical electric vehicle about less than 1/10 of a mile. So if you had a 200-mile range initially, you ran it down to nothing, and you want to replenish that 200-mile range on household current, we're talking about over 2,000 minutes or about 36 hours or more than a day and a half. You're not going to use your car every other day. So that's just simply not going to work. Fortunately, you're probably aware that the 110 voltage that comes into your house is actually two different 110 lines that can be combined into a 240 volt line. Now, when we double the voltage, we can also double the current. So doubling the voltage doesn't have the charging time, it roughly quarters it. You get 4 times as much energy in a given time. Now you're adding not quite a half a mile per minute, and you can charge this from 0 to 200 miles in about 6.5 hours. So you can use your car all day and charge it overnight. That's doable for somebody who uses their car every day around the house, commuting to work or what have you, and can charge it overnight. But what if I want to go further than 200 miles and I want to do it efficiently? Now we're getting into the realm of what's called the DC fast chargers, where we pump this up to 480 volts. Now we've got this down to, we can add 200 miles of range in about an hour. Maybe not terribly convenient, but I'm going to have to stop after three or 4 hours and plug my car in. I guess I can have breakfast, lunch, dinner, whatever the appropriate meal is for the time of day while it's charging. It's doable, but it's still not what we're used to. And we really have Tesla, our friend Elon Musk, to thank for this. I'll talk about how he does this. He bumps that up, still using 480 volts, but he raises the current so that now instead of 50 kilowatts, we're pumping 140 kilowatts into our vehicle. Now we've got it down to 21 minutes to add 200 miles of range. Still, well, maybe if I go to Costco and I'm sixth in line, it'll take me 20 minutes to get fuel, but that still is not what we consider typical, but that's.
Those are the ones that he has out right now, like in the Wawas. that
Yes.
have a Tesla one.
Yes,
Okay.
and I want to talk about why he can do that, because the enemy of batteries is heat. And it's not the heat that it generates while it's running, it's not the heat while it's parked, it's the heat that's generated while charging. Anytime you push current through components of finite resistance, you generate heat. And these batteries do not like heat. If they get too hot, the electrolytes are flammable. It's bad news if they catch fire. Now, fires are not that big a deal in terms of frequency. In fact, electric vehicle fires, even on a per unit basis, are still less than gasoline fires. But they get the headlines because they're new. And they do actually, they're harder to extinguish. So it's there are legitimate concerns about it. So how do we cool the battery while we're charging it? Well, the Nissan Leaf, which until recently I think was the largest selling electric vehicle in the world, I think it has since been surpassed. But you hear about Teslas and things like that. Nissan actually had the best-selling one. It uses an air-cooled battery, and it can only use level 1 and level 2 chargers because you just simply can't get the heat out fast enough to charge it faster. Nearly every other manufacturer except Tesla cools the battery pack by what I call indirect cooling, meaning battery pack is a sealed container, and what they do is they have plates that butt up to the battery pack with coolant running through them to extract heat. So this allows you to get to the DC fast charger at the third level we talked about, but still, since you're relying on the thermal conductivity of the battery and the electrolyte to pull heat from the center of the battery, you can only do that so quickly. It's Tesla's big innovation is to circulate coolant among the cells and actually pull heat out, which enables them to go to that very high speed charging. And that's why those high speed chargers are can only be used, at least in their high speed mode, on Teslas, because only Tesla has this direct cooling ability. So there are various legislative actions being taken to allow other vehicles to plug into the Tesla supercharger, but if they do, they still won't be able to use the very highest charging rates. They'll be limited by the ability to cool their batteries. I put this slide in here, and this is probably the only one I'm going to read word for word. Research engineers are now at work seeking new and satisfactory fuels which can be obtained at reasonable cost to take the place of our rapidly decreasing supply of petroleum from which gasoline is distilled. I often ask if anyone wants to take issue with that. Nobody really disagrees with that. This came out of a textbook I have on my shelf from 1924. So in 2 years, we're going to celebrate the 100th anniversary of us running out of gas. We've been running out of gas for a very long time, but what keeps happening is we find new and innovative ways to extract more of these fossil fuels. Maybe we're somewhere near the end of that. We clearly have reached the point where it's not as cheap as it used to be. And actually if we're going to continue to have mobility, we need to consider these alternatives. I've talked a lot about electric vehicles, particularly battery vehicles. There are at least 40 companies out there selling battery electric vehicles. There are at least 300 claiming to be in the business of selling electric vehicles, but they have not yet built or sold one. So there's going to be a lot of shakeout in this space in the next few years. It's going to be really exciting to watch. But The internal combustion engine isn't going away, I've already mentioned. At least, even if we stop selling them today, it's going to be around for a couple of generations. And there are other innovations we can use. We can burn, in addition to fossil fuels, we can burn other liquid fuels like alcohols. And we can even look at gaseous fuels. Again, compressed natural gas and propane are also fossil fuels, but they are not as carbon intensive for unit energy as gasoline or diesel. And we have this other interesting gaseous fuel, hydrogen, which in its combustion does not produce carbon dioxide at all. Its only combustion product is water. But we've tried that, and I want to talk about one other way of using hydrogen to make electricity run an electric motor, and that's the fuel cell. Let's look at the hydrogen internal combustion engine. This is what comes to mind. That's the Hindenburg exploding over Lakehurst, New Jersey in 1936. Anyway, that's what comes to mind. I've done a lot of reading on this, and a catastrophe, no doubt, owed to humanity, all of that. What you see burning here, interestingly enough, is not hydrogen. Hydrogen flames are invisible. What you see burning is actually the aluminum-based paint that's coating the outside of that structure. That's what's incandescent. But the other thing that this illustrates rather nicely, it's being carried up by the hydrogen as it burns, and that's the key word. Hydrogen is lighter than air. Hydrogen flame literally burns up. It burns up and away from you. The people are down here somewhere. And interestingly enough, everyone who stayed on board and rode that to the ground survived. The fatalities were all among crew members who were in the superstructure when this happened, and people who jumped from the gondola trying to escape the fire. Again, not saying it's fun, but the interesting thing about hydrogen is Argonne National Laboratory did a study on hydrogen as a fuel and concluded that it is at least as safe, if not safer, than gasoline and diesel fuel. And I like to have this thought experiment. Suppose that you lived in a world that was the same as the one we're in, but for some reason, hydrogen was the fuel we all grew up on, and gasoline was the new kid on the block. And your job is to go to federal, state, and local governments and convince them to let you put 100,000 gallons of this new fuel under every major intersection. This fuel that is flammable and explosive, just like hydrogen, but in addition, it's also toxic. It's also potentially carcinogenic, it's potentially tetragenic, and if it leaks, it contaminates groundwater. If hydrogen leaks, it literally goes up. There's an argument that hydrogen is also a greenhouse gas, but not nearly as potent as the others, so it's not totally harmless, but it is a pretty safe fuel. But how do we get past this? Well, one way, we could take a hydrogen-fueled vehicle and maybe get a celebrity to pose in front of it for us. That's what we've done here with the California Hydrogen Highway Project from many years ago when this fellow was just recently the governor of California. General Motors actually made a couple of hydrogen-powered Hummer H2s. Now, hydrogen-powered in the sense that these were internal combustion engine vehicles that ran on hydrogen. Now, the advantages of hydrogen internal combustion is that the only combustion product is water, but it's still not a zero emission vehicle because some amount of oil is needed to lubricate the piston rings, and some of that oil and the valves, and some of that oil gets into the combustion chamber and combusts. So there are still some very small carbon emissions in a hydrogen internal combustion engine. And because of hydrogen's high combustion process, high temperature combustion process, it interacts with nitrogen and oxygen in the air and creates these oxides of nitrogen, which are another harmful emission. So it's not truly emission free, but it's much, much less than with fossil fuels. We can electrolyze water to produce hydrogen and then burn that hydrogen to produce water, and in that cycle have no carbon footprint at all. It's possible.
What's the energy input versus the energy output?
That's obviously higher going in and coming out, but if you're doing it with, say, solar or wind power, and you're using the excess that would otherwise you weren't using for anything else, you can think of hydrogen as an energy storage medium in that regard, much like charging a battery. If you have the infrastructure and you have the electricity, you can do it. Disadvantages, we're still limited by the Carnot efficiency if we're burning the hydrogen. So storing a significant amount of hydrogen requires either very high pressures, typically 5,000 to 10,000 psi, or very low temperatures. We're talking cryogenic temperatures to liquefy the hydrogen, both not something the consumer is likely to be very comfortable with. And unfortunately, although we can electrolyze water to make hydrogen, 95% of the hydrogen produced commercially today comes from reformulating natural gas and venting off the CO2. So not there's what we call green hydrogen and not green hydrogen, I guess. And most of the hydrogen we have today is not green. But there's a more efficient way to use this, and that's not to burn it at all to make heat and then make electricity. What we do is we react the oxygen in the air with the hydrogen in our from our storage facility in such a way that we directly transfer the electrons to make that chemical bond through a conductor in such a way that we're not generating heat, generating electric current directly. This is called a fuel cell. It does not have the problem of the Carnot cycle. And again, these fuel cells, they don't have a thermodynamic efficiency limit to them. Now, of course, we're passing current through wires of finite resistance. Our transfer membranes are not infinite. They have boundaries in which there are inefficiencies. So we don't get 100% efficiency. But typical efficiencies for these fuel cells in terms of the energy content of the hydrogen versus what we get off in electricity, 98%, fairly typical. So we can make use of the energy of the hydrogen much better by means of fuel cell. And why would we want to do this? Well, Toyota, for one, has given us this nice chart where we look at how far a vehicle travels on the average day as the x-axis, and the amount of that vehicle to carry is the y-axis, or the payload, if you will. And what they basically said is the blue section in the lower left, that's the battery electric vehicle section. This is great for light vehicles like cars that don't go very far in a day, like a daily commute. This is great for that, but when we get into commercial vehicles that are carrying large amounts that we want to go to stay on the road a very long time, like buses and trucks, or to carry large amounts of cargo like trains, fuel cells begin to make a tremendous amount of sense. And in fact, in Germany, they just, I believe, inaugurated the first dedicated fuel cell train on a commercial route that is now operating. And you can look that up, the fuel cell train. The nice thing about a train is, since it runs on tracks, you know exactly where to put the refueling stations. But even commercial trucks that will generally run between fixed points, it's easy to relocate the filling stations where you need them. But when it comes to the situation where when you're moving on something other than land, like water and air, now the weight of the energy density of the fuel becomes a significant concern, and we're probably still stuck with liquid fuels in terms of aviation and ocean shipping type operation. Not saying you aren't ever going to see an electric plane or an electric boat. They're out there, but they remain, their practicality is highly suspect in terms of commercial, things like commercial aviation. I don't think we're going to see a 500 passenger electric plane in the near future, or possibly, well, probably not in my future in any case. That was it. I want to take your questions and comments, and there's my email address again in case you forgot to write it down and you have a question. You're going to moderate for me?
Yeah, and what we'll do is we're going to alternate questions between the present in-person audience and the online audience. So we'll take the first.
The magnets and the rare earths, are we going to be to a place where you say that's going to grow versus the induction? We're going to get to a place where we can't get the raw materials. Or it gets so expensive that it prices it out.
So the question, should I repeat the question, or are the microphones operating? Okay, the question was the source of the rare earth materials for the magnets. What's going to happen as they grow as rapidly? That issue has been around for a couple of decades. And in fact, one of the things I worked on in General Motors, my last some of my last projects were on these electric motors and specifically the rare earths. There has been a diversification of the source of rare earths in 2010 or so. About 95% of the rare earths came out of China. That's down to around 75, 80% now with other mines operating around the world. And there are a few.
A lot of those are in conflict areas.
Yes. Essentially, it's going to come down to what the people are willing to pay for it. I mean, I don't have a great insight as to where that's going to come from. There are plenty of rare earths out. In fact, the total weight of rare earths in the earth crust, if you add them all up, the dysprosium, neodymium, terbium, et cetera, is about equal to that of copper. Copper is hardly considered rare. The difference is these rare earths don't concentrate in useful ore bodies as readily. So there are fewer places where it can be profitably mined.
You know, to get a pound of some of these rare earths, how many tons of ore?
Oh, I was out at.
Roger Trivett did a program on that about 3 years ago.
I was out at the rare earth mine in California several years back, and I knew what the number was then. But we are talking remarkably. When we talk about something like iron ore and hematite, we're looking at 60, 70% iron in those things. These rare earth ores, we're talking about 2%, 5%. Not where it's at. So you're moving a lot of rock to get a.
There's got to be energy costs in refining
Yeah.
that ore.
All right, Chris,
Are rare earth permanent magnets readily reusable or recyclable?
Hypothetically, yes. And in fact, again, there's a couple of commercial entities out there looking into harvesting them from the waste stream. It should be, but I don't know exactly where that stands. But again, recycled steel sells for tens of dollars a ton. The materials in these magnets, which are now, it's neodymium iron boron, and I forget what the exact amount, but it's, I don't know, 30%, something like that, rare earth. It's the richest concentration there is to mine somebody, and a lot of people are working on it. And I think you're going to see, much like iron and aluminum, as the waste streams become more mature, you're going to see much more harvesting of these magnets. And by the way, they're not just in cars, they're in here, they're in all of your little, it's just a remarkable coincidence. I'll show you this because I stuck it in my pocket as I was going out. This is my electric toothbrush. That's a rare earth magnet on the bottom that oscillates my Sonicare toothbrush. I stuck it in my pocket as I was going out the door. So they're everywhere. And somebody's going to figure out how to harvest it, which shouldn't be so hard because magnetic separation should be extremely efficient for getting these things out of the waste.
Is there an online if you were gonna?
I just took one.
Oh, okay. I noticed on your chart where you showed the crossover between the number of ICE vehicles and electric vehicles sold, you had about at 2037.
Roughly, yes.
But all these companies are saying they're going to stop building gas-powered cars by 2030 or 2035. Are you not taking that in? In other words, are you discounting those claims
I think
and thinking they're going to keep building them longer?
Short answer. Okay. We worked in the industry for over 30 years. There's the claim and then there's what they actually do. I hope that answers your question.
Can we,
I'm going to take it online.
it was kind of follow up on that question as well. But from both of your slide, I counted like in that slide where you show which countries accepted legislations.
Mhm.
By 2035, it looks like at least 50% of countries, right?
Yeah.
Ban or planning to go 100% electric vehicle sales.
50% of countries, but remember, 50% of sales are China and the US.
And China was 2035.
China was about 30%,
Yeah, so
but the US has no coordinated national goal. So
it just seems like if just China goes, it should.
it should be, it will push it in that direction. Let's go to an online one.
If hybrids are more complicated in parts, why are they reasonably priced?
Because they have an underpowered electric motor and an underpowered gasoline engine. Is the short answer. It relies on the interplay between those two. It's a small engine and a small electric motor. So they're individually less expensive than a vehicle that has to run on one or the other. And there is a nice counterbalance between them. As I mentioned, the internal combustion engine generates high power at high speed. The electric motor generates high power at low speed. So you launch with the electric motor and then the gasoline engine motor takes over as the vehicle gets up to speed. You have this very nice synergy between the two types, so you can get away with smaller motors. But you also have the two, you have the big battery, you have the fuel tank, you have all the electronics. Toyota does not say, and by the way, the #1 selling hybrid in the world is the Prius. They don't say what their profit margin is on the Prius and never have. So you can see what they sell it for. I can't tell you if they're making money today or if they've ever made money on it. I don't know.
But they're Japanese.
My wife got me, I have a Prius, my wife got me a nice bumper sticker that says cool Prius, nobody.
Says nobody, yes.
What are your comments about the use of solar power and increasing the technology of solar power, either by itself or in conjunction with some of these other sources?
I think that solar power, again, there's not going to be one answer. But the advantages of solar power are tremendous. I see it going in larger and larger installations every day. I see more efficient solar panels coming out. I see better technologies for keeping them clean so that they continue to generate energy. And they have the tremendous advantage, unlike wind or geothermal or hydro, in that there are no moving parts. So from a mechanical standpoint, they're tremendously easy to maintain. I won't say maintenance free, but I think you're going to see large swaths being taken over by solar panels even more than you've seen today.
Yeah, because the sun is, after all, a rather large source of energy, including ourselves.
Yes, it makes a great deal of sense to me, to the point where I put solar panels on my condo in Ann Arbor. I generate my own electricity during the day, and the Detroit Electric DTE actually pays me a fraction for what I pump back into the grid, not what I pay them to extract it. Much like the regenerative brakes, they don't pay me the same when I push it their way. And they're trying to change the law, so they have to pay me even less. So you have this, you have the mature technology competing with the new technology. That's an economic question.
And again, so let's thank him for